speaker is Alice Guionnet from the École Normale Supérieure de Lyon and ENS, and we really thank her for giving a talk in this conference. And today she will speak about matrix models, topological expansion, and operator algebra.
Okay, so thank you very much for the invitation to talk here. It's of course very emotional to think about Vaughan. And okay, I will do my best for this occasion. Okay, so I would like to talk about some work we did together, but also some kind of long-term project I've been pursuing around non-commutative entropy and matrix models. And before that, of course, now I can't change my slides anymore. Okay. Yes. Okay, so I realized why Arthur was always taking pictures, and I mean, he always has lots of great pictures, and I could only find this picture of Vaughan, which however, you can see where it is. It's just behind there is a Tongariro. So it's the last time I went to a conference with Vaughan in New Zealand, and Vaughan super kindly told my husband and I we should go and hike there. And he even came so that to make sure that we do it. And this was a beautiful hike, and we were really a beautiful time altogether. So this is Vaughan in yellow and the Tongariro at the behind. Okay, so why can't I? I'm not sure why I can't. I cannot easily change the slides. I'm not sure what happens. Okay, so I'm going too fast, but it's okay. Okay, so I just wanted to tell about the kind of program that I've been trying to pursue, which is around the entropy program in classical probability. And in classical probability, there are kind of ideas that, so if I go behind that, if you look at the empirical measures, any kind of probability measure can be approximated by empirical measures. So that's the Birkhoff theorem. And then you can ask other questions, which are, well, if you can approximate any kind of measure by empirical measure, what is the probability that you approximate a given measure? So for instance, take gamma to be the Gaussian law, and you take n independent copies of this Gaussian law, and you sum it up, so you get this kind of empirical measure. And you ask what is the probability that this empirical measure approximate a given probability measure mu. So d is some distance on the space of probability measures, and you're allowed to have some error delta, which is positive, but going to zero after n goes to infinity somehow. And so the answer is well known, and it's Sanoff's theorem, which tells you that this probability should be of order exponential minus n times the entropy. And here h is just the relative entropy. And wonderful, it works. And another point of view on this kind of thing comes from statistical mechanics, which is to consider Gibbs measure. So Gibbs measure is here, so it's maybe not so well visible, but somehow you take the same law gamma, you take n independent copies, and you consider the integral of some exponential n beta times some continuous function of the empirical measure. Okay. And this is usually what we call free energy. Once we take the logarithm and we take the normalization and we try to compute the limit when n goes to infinity of this kind of object, or we can consider the associated probability measure, which is to change your product measure by adding some density. Okay, and this kind of probability measure is describing many physical systems, and you would like to understand what is going on when n goes to infinity. What is the behavior, what is the phase transition, and so on. And in fact, these two kinds of questions are, of course, intimately related, because if you take G to be the distance to some given measure, so it will be kind of continuous function, then typically what you will get is exactly this, this measure of the ball if beta is very large. Okay, typically your probability measure will concentrate on some small ball around your given measure. So this type of point of view is very general, but somehow this is what I've been trying to reproduce in the non-commutative setting, where we have now random matrices instead of just Gaussian entries. So of course, so I put here a big slide to say what is the analog of a probability measure, but in front of this audience, it's quite clear what should be the analog of probability measure. It's just a threshold state, so that you see at the linear functional on the set of non-commutative polynomials, but it could also be more general test functions which are bounded. And if you follow the previous scheme, so the first question was to know, so if you take matrices, so I will take self-adjoint matrices through the talk. And you look at what I call the empirical distribution, so which corresponds to the threshold state which associate to a polynomial the trace in these matrices, and you normalize it. And you ask whether you have the analog of this Birkhoff theorem. And as I imagine everybody here knows, there was this breakthrough paper last year which say that it's not true, that you have non-commutative laws which cannot be approximated in this way by bounded matrices. So I stress that because, of course, it's all the questions of entropy and Gibbs states are also impacted by this kind of problem that you know now that there are states which cannot be approximated by these matrices, but actually it's not clear yet what kind of states this are. Or, I mean, I would be happy to have any information about the kind of states that cannot be approximated by matrices, because this would be quite helpful to understand better. By the way, do not hesitate to interrupt or ask questions if I am unclear, whatever. And okay, so this is again blocked for some reason. It's kind of painful. Okay, so about random matrices. So before looking at what you can approximate with random matrices, it's good to recall what random matrices are doing typically. So if you take random matrix following the GUI ensemble, so it means you take a n by n matrix and you fill it with independent Gaussian variable, except for the symmetric constraints. And so in this case, I take complex entries for unitary ensemble, but it would also be true actually if I would take real entries. And so what Voiculescu proved is that in this case, if you take D matrices and you look at this non-commutative law, you can take the expectation, but anyway, the convergence would almost surely, then you have convergence towards some state, some non-commutative law, and this is the law of the free semicircular law variables. Okay, and in fact, as in the talk by Vaughan, this non-commutative states is characterized by non-crossing partition, in the sense that you can think about, if you have a monomial, you can think about the letters as dots on a line. And if each letter is associated to a color, so here I have only red and blue. So for instance, X1 will be represented by red and X2 by blue dots. Then this guy will compute just the number of non-crossing pair partition, where you can only pair points with the same color. Okay, so that's kind of the first point. And then if you start to ask about the entropy, so this entropy was introduced by Voiculescu, and so you could ask, so if you take x1, x and d to be independent GUE matrices, so what is the probability that the non-commutative distribution goes close to some other threshold state than the semicircular law? And so what we proved, so some 20 years ago, is following some proposal by Voiculescu that we cannot actually compute this limit. And this actually appears to be pretty hard in view of this contradiction to Cohn's embedding question, because I mean, you have to understand how this existence of these bad states is realized somehow analytically. Well, yeah. So what we proved is that the entropy, this microstate's entropy, is bounded by some other entropy, which is chi star, which I will not define, but which is the analog of the relative entropy. So you have a bound from above for this entropy, and you have actually equality, but only for very nice laws tau. And these laws, actually, we have a very constructive way to define them. There has to be solution of what is called a stochastic, well, a free stochastic differential equation. So you have your matrix, your operator, your limiting operator, which should be given by the limit of a GUE matrix, but which is filled with Brownian motion. So this is called the free Brownian motion, plus some drift. And your law should be the distribution at time one of this solution. And here the important point is that you assume that the drift is smooth. And because smoothness implies somehow that you have uniqueness of the solution. But in fact, this chi star is the L2 norm of this kind of guy from 0 to 1. And in principle, you know that the entropy, the chi star entropy, will be finite as soon as the L2 norm is bounded, whereas what we know to prove the lower bound only when this k is smooth. So this is kind of the discrepancy between the lower bound and the upper bound that we could never really manage to solve. And in fact, so when we look at the analog in one dimension, then we can exactly solve this discrepancy. We can prove that somehow this kind of solutions is dense, and so we have the lower bound for all threshold state, but in the general case of several matrices, this is still open. And here you see that somehow you have to understand why there are some states that you cannot approximate by this kind of solutions. But that's kind of still very much open question. So of course, in the case of one matrix, everything can be computed because you have the joint law of the eigenvalues, and this was shown by Dan Voiculescu, and then proved also in the sense of large deviation with Gerard Benahous and myself. But so in this case, everything is known. And you have again, in this case, the upper bound and the lower bound for the entropy, for the microstate entropy, and the microstate entropy is given by this formula. Okay, so here we are blocked, but then you can wonder, well, what about the statistical mechanics kind of approach? And what would be the statistical mechanics kind of approach? So you would look at random matrices. So again, D random matrices. And again, you have the law of the GUE, so you take independent GUE matrices, but then you add a density. So you want to change somehow your law and see what happens. And eventually, so I add this, so you may ask that the operator norm is bounded to make this a well-defined probability measure. I will not talk about that later, but this is something we can do if things are not well defined. Okay, and then if you look at the question in statistical mechanics, so the kind of natural question is whether you can define a limiting threshold states for this kind of matrix model. So if you look at this probability measure and you look at the trace of polynomial in these matrices, so can you prove that this converges? And then what can you say about the limit? And again, as before, so if I could also generalize a type of potential to take tensor products. And if I would do that, I mean, also I would be able to take somehow in the potential the distance to some threshold state. And so this would be kind of equivalent to Poincare control. And we can do actually this kind of generalization in many settings, but I will not discuss that later. Okay, and so, I don't know why. It's very strange. For some reason, I can't again switch slides.
Are you using the arrows?
Yeah, I'm using the arrows in every direction.
Try clicking on the page. Just try clicking on the page.
Ah, yes. Thank you very much. Okay, I have to click on the page and then the arrow. Okay, great. Thank you very much. Okay, so then what can we say about this kind of matrix model, about the limits? So what I will discuss is what we can say in the perturbative case. So it's what is called in physics the high temperature case, because you can think about beta as 1 over the temperature. So we can understand very well the perturbative case where this beta is small, so you have kind of small density. And we will see that this is related with the combinatorics of maps, and this is very close to what Vaughan was describing. Then there is the idea that somehow the perturbative case, what you can see in the perturbative case should generalize until you have a phase transition. And we could not really prove that, but we could prove that everything goes through when you still have a convex potential. And in this case, you don't have a phase transition. So, but phase transition, I would just mention it, but we can only do very easy models. And then, so recently with Edouard Maurel Segala, we are trying to understand what happens when beta is very large. So I will mention that at the end. Okay, so let me describe the perturbative case and how it is related with the combinatorics of maps and planar maps and non-crossing partition. Okay, so what are the maps we consider? And this is also what will be related with what we did with Vaughan. So what we consider is vertices which are colored, so the color are related with the different matrices, and so this will be a vertex. So you can think about a vertex like really a vertex on half edges which are colored. So these vertices are in bijection with monomials because they have a root, so which is a distinguished half edge. And they are drawn on the surface, so on the plane. So somehow this gives you some order. And so for instance, this vertex, if you think that the red is the color of x1 and the blue is for x2, so this vertex would be kind of in bijection with x1 square, x2 square, and then x1 to the 4, and then x2 to the square. Okay, so you can think that there is kind of bijection between vertices with these colored half edges and monomials in non-commutative elements. Okay, and the maps that will be related with the matrix models are so the number the enumeration we will be interested in is the number of maps that you can build over several such vertices. So here Ki, so these vertices I call them stars of type Ki. So namely, I will show later a drawing, but I should have had one, but imagine that you have only one vertex. So if you look at the planar limit, so the case G equal to 0, what you will count is the number of possible matching of the edges of the same color so that the vertex at the end can be drawn on the plane. So this is equivalent to look at pair partition, which are non-crossing, and with these color points. Okay, and but we will consider the case where we can have several of these guys, and we will count the number of graphs which are connected and which are created by matching the half edges of the same color in such a way that at the end we get to some planar drawing. Okay, and so the relation with between matrix models and the enumeration of maps is very well known in physics for a very long time. So after the work of Toft and Brezin, and Parisi and Zuber, what they showed is that somehow formally, and this is what is important, you can see that this integral is going to be given by a generating function for the enumeration of these maps. Okay, so what does it mean formally? It means that if I take the differential with respect, so here V is some sum of monomials with some weights, TIs, and when you differentiate this left-hand side with respect to the TIs, and you take them at Ti equal to 0, then you should find that this is equal to this, the term which corresponds to the same derivative on the right. Okay, so that's the formal equality that was proved long ago. And so this shows that somehow you have a hope, which is actually more than a hope, to compute this kind of enumeration of drawings. For instance, if you look at the case G equal to 0, just by taking the limit when n goes to infinity. Okay, when n goes to infinity, because you have this term, you see that the only terms which will survive will be the term with G equal to 0. Okay, and so what you will get is some generating function for these numbers taken at G equal to 0. So for the numbers of planar maps built over these stars. Okay, and if you look at the correction, then you will get maps with genus 1, but somehow what is more interesting in free probability is the limit when n goes to infinity, where you get only planar maps, case G equal to 0. Okay, and so what we proved with Edouard Maurel Segala is that in fact, under quite mild condition over the potential, and provided the beta here is small enough, but of order 1. So provided, so either we put back this indicator function that the operators stay bounded, or we assume that somehow the potential is kind of convex, at least when, okay, it's kind of convex. Then what we proved is that indeed, what I showed is not only formal, you can speak about limits when n goes to infinity, and these limits coincide with the formal equality. Okay, so this is somehow what we proved, and this was kind of nice because this allowed us to use lots of heuristics from physics, which were based on this identification of Itzigson-Parisi and Zuber, Brezin, Itzigson-Parisi and Zuber, and Taft between these two worlds of matrix models and map enumeration. Is there any question? Okay. Okay, so maybe I can say a word on how this is done, because it's quite short. I mean, the idea is to use concentration of measure. So because we assume that somehow this probability measure has a log concave density, we know that somehow the trace, the non-commutative law of this matrices self-average. And we use that to obtain equations for these averages, which are called the Dyson-Schwinger equation or loop equations. And the big point is that when beta is small enough here, we can show that this equation have a unique solution. And so this is enough to conclude that you have limit points, and somehow the limit points are the unique solution of some equation. And then you see that this equation is also satisfied by the generating function of maps. That's somehow what we do. I just point this out because somehow it's kind of related with kind of equation that Jon was mentioning. So we have kind of complicated equation, and at some point, well, we need to show that there is uniqueness of the solutions. Okay, and this equation actually were known before in combinatorics as the third surgery. Okay, so let me come now to the work with Vaughan, which is related with this perturbative setting, but what we did was to extend this type of approach to loop models and well, planar algebra. So I will restrict myself because it looks nice to temporary elements. So what are they? So it looks really much like what Jon was talking about. So temporary element, it's you have a box and you have boundary points, and you have a pair partition between these boundary points, and then you color this. So you have a root here, and you color the pair partition like a checkboard. So you have a shading. Okay, and so then what the loop model for this kind of temporary element is again a bit like Vaughan, like what Jon was talking about. It's a generating function of numbers. So here you are summing over all possible maps that you can build by prescribing. Now you don't prescribe stars, but you prescribe temporary elements. So here, for instance, I have 3 types of temporary elements. I have this one, and I have these 2 types of possible temporary elements. And then I look at all the possible ways to match these endpoints of my temporary elements in such a way that the shading is respected. Okay, and so a loop model is a trace which associates to a temporary element S, some real number, which is just the sum over all the possible number of this other element. So here S should be thought about this, about this element. And you sum over all possible numbers of these 2 types of elements here. And you have a weight which depends on the number of loops. So it's really much like what Jon told you about. So the number of loops here would be the number of meanders somehow. But we have a more complicated system because we allow to have many temporary elements, whereas Jon was only considering one. Okay, so that's kind of model that we got interested in. And so what we proved with Vaughan is that actually, and we can approximate this kind of matrix model by random matrices. And this we can do for delta, which are the possible value of the index in subfactor theory, which are these 2 cos of pi over n or greater than 2. Okay. And the reason, one of the reasons why we were interested by that, so this is related to the well-known Potts model on random graphs. The point is that by doing this representation in terms of matrix model, we could compute more things. Okay. So in fact, we could compute these quantities as long as S was one of these elements. Okay, if we could compute this quantity for all elements, I think this would solve somehow Jon's questions about meanders, because then we would just need to sum over all these possible elements and take the derivative somehow at delta equal to 0, and this would give us the number of meanders. But we can only compute that for a specific temporally elements. Okay, and maybe let me give you some details on how this kind of thing can be done with matrix models. So it's a bit, again, in the spirit of Jon. So the idea which was proposed in physics, in the case where delta is some integer numbers, is that you can, you have a matrix model for this kind of quantity when beta is equal to 0, which is given by considering special polynomials in your random matrices. So here I cannot really focus on that. So here the idea that you attach to a temporary element a polynomial which will have the degree given by the number of boundary points, and the idea that you impose these monomials to have the same index if they're related with a partition, a pair partition. Okay. So for instance, here, if I want to model this temporary element, what I will ask is that this index is the same as this one, and this index is the same as this one, and this is the same as this one. Okay, so this is exactly what I do, and then I sum over all these indices. And then you can see that if you compute the expectation of this kind of guys, and you use Voiculescu's theorem, then somehow the expectation will be given by the sum over all the possible diagrams, which are planar, and they will have a weight which will be m to the number of loops. Okay, so this is very much related with Jon talks, and the detail for that is quite easy to see. So you want to compute this mean. So you write what this is, and for each of these terms, you can use a Voiculescu result. And what Voiculescu tells you is that this expectation will be the number of, will be given by non-crossing pair partition, where you pair only indices which are the same. And so you see that if you have a partition on the bottom here, this pairing implies that G has to be equal to K. Okay. So here you see that in this drawing, I must have I equal to K and G equal to K. So all indices has to be the same. And what I will do, I will have n choices for these indices. So I will have n to the power 1 for this, and I will multiply then by the number of these possible drawings. Okay, so that's how it goes, but this is for m integer, and what we could do, thanks to Vaughan's construction of planar algebra of a bipartite graph, was to generalize this to m taking values delta, which are the possible indices for insert factors, and which are actually the parent Frobenius eigenvalues for the adjacency matrix of bipartite graph. So indeed, how do you do this construction here? So you change, before we had this specific polynomial attached to the value m, and we want to change it to some value delta, which is continuous, because somehow at some point we want to take derivative on things like this to isolate the case where you have only one, for instance, one loop. And so what we do is that we replace this sum by a more complicated sum, where now the variables are indexed by edges. So the edges of a bipartite graph, yeah. And in such a way that, so this bipartite graph has an adjacency matrix which has the eigenvalue delta for some eigenvectors. Okay. And so actually that's the condition that this implies that delta has to take one of these values. And then you sum all these possible products over all the possible choices, where you assume that for the edges here are going to give you a loop. Okay, so you assume that the first vertex goes from the same one vertex to the same vertex, and you take well-chosen weights. And so then when you do the same kind of computation as the one I just showed you with Voiculescu result, but with more complicated matrices, so which now are not GUE matrices, but are rectangular matrices with dimensions which are chosen according to this eigenvector. So once you do the same computation, then what you will get is exactly this generalization, but the trace of this kind of polynomials will be given as a sum of all these possible meanders, but this time the weight will depend on delta. Okay, so that's very nice. Actually, I don't think it was foreseen really in physics. Well, some physicists told me that Kostov had thought about something like this, but it was kind of a very nice idea, I thought, to get to continuum values of delta, and to be able to go forward to use this kind of methods to understand better the combinatorics of this kind of maps. So I think it was really nice. Okay, and this is left as an exercise. And so after that, well, we could also look at matrix models, but this time you have a more complicated density. And again, you look at some beta i's here, which are small enough to have this kind of perturbative regime. But then you can use exactly this type of construction to have a continuous fugacity. Okay. And then we used also this result, well, without actually any density, to show that the limit of this threshold state gives you a factor, and actually you can construct a torus of factors with this index delta square, thanks to this type of threshold states. And so this was already found by Popine earlier with some parallel techniques. Okay. So So that's about the work with, oops. That's about the work with Vaughan. And is there any question about that, about perturbative setting? Otherwise, I can continue on. So what can we do in non-perturbative situations? So we can do much less. So I should finish on time. And so what can we do? So first, as I said, we can more or less extend everything to the case where we have a strictly convex potential. I mean, it's not easy. You need to use much more analysis, but somehow it's expected that you shouldn't see any change in this kind of situation. So here again, P was this law of the GUE. And then, so what we can see is that if this potential remains strictly convex, so in the sense that if you take the trace and deviation in any dimension, when you apply it to matrices, it will be bounded from below. And then you can show that this convergence of the matrix model still holds. And actually, this limit will be the kind of analytic extension of what you have for beta small. I mean, there is no phase transition. Everything is kind of analytic extension. You can also show that the entropy actually is equal to the microstate entropy. So this was two very nice work by Dabrowski and Jekyll who showed that. I mean, what I showed you that we did with Philippe Bian and Mireille Capitaine would not allow to show this kind of thing because the equality that we got were for very mysterious threshold states. Here it's kind of very, very nicely defined. And what we could also show, so in some series of paper with Dima Shlyakhtenko and then Johan Dabrowski and then Jekyll, is that so if you look at this limiting threshold states, somehow the C-star algebra and the von Neumann algebra that are associated with this threshold state by the GNS construction, so they are isomorphic to the one when beta equal to 0. So to the one of the three variables, and we could prove this kind of thing by constructing some analog of transport maps. So that's what we did. And somehow the idea would be that all this should remain true until you get to the transition, okay? And so this is, so convexity is ensure that you have no transition. So what could we say about transition? So there is not much to say because in general, we don't know how to handle this kind of, the existence of the kind of limits of matrix model. So except in some cases. So if you have one matrix, of course, we can get the limit of matrix models, but this is not very interesting at the level of operator algebra. We can do two matrices with a kind of simple interaction. So this is what is related, if you look at the enumeration of maps with the Ising model. So here it's with genus 1, but I mean, I could have drawn the drawing in genus 0. So in this case, we have this convergence for all values of beta, but this is one of the rare cases where we can do that. And a priori, I mean, my hope that I discussed quite a lot with Vaughan was whether something nice could happen at the phase transition. And Vaughan was kind of skeptical, and I'm starting to be skeptic too. In the sense that something is going on at the phase transition, typically you would expect that the C-star algebra would change. Okay, so if you look at beta small, you know that the C-star algebra associated or the C-star algebra of free semicircular law, so they are projectionless. But if you can cook up the parameters here so that for beta large, somehow each matrices will be in kind of wells like this. And so at some point, the spectrum will disconnect. And this allows you to create in the C-star algebra projection. Okay, so what seems to happen for the time being is only that the C-star algebra will change because it will get some projection. Okay, so what are we working on recently around this kind of ideas with Edouard? So we are trying to understand what we can say about this kind of limit in the most general context. And what we could get is some nice, so I forgot the beta, but we should have again the beta. So some nice hypothesis on the potential V, so that we can have limits of matrix models. And this is basically some condition which allows you to say that your matrices will stay bounded. So we have kind of general solution criterion for that. And we can also show that the limit is satisfying some Dyson-Schwinger equation or loop equation. But in the case where beta is large, as before, there are several solutions in principle. So you cannot infer from that you have limits, that you have convergence of your matrix model, and it's not clear what properties it should satisfy. So we worked on some specific models, and this will be my last slide. I will be just on time. I think I have until 50 yes. Yeah, so it will be good. So
Alice, sorry, yes, 50.
Okay, great. Okay, so I'm nearly finished. Okay, so we looked at so this time low temperature expansion. So imagine now that you have a potential which have a beta which is only on the polynomials in one matrix. Okay, so if W is equal to 0 here, you have just independent matrices, and so everything is asymptotically free. So there is not much to say. But if you have just an interaction which is in a smaller scale, and your V or minimum in some point xi, where they are convex, then what we could prove is that again you have convergence of the matrix model when beta is sufficiently large this time, and somehow the limit will be a function of semicircular law. Okay, so it's kind of a similar result actually than when beta is small. We are looking at small perturbation of GOE matrices. Then we look at the case where we have, so it's not as it's more complicated, but in the case where we have several minimizer, then somehow what happens is that the matrices will concentrate into block diagonal matrices, each block corresponding to some minimizer. And actually we can compute the mass of each of these blocks. Okay, and we need some assumption on the interaction here, which is such that this vanishes when you are somehow at the minimizer of these guys. And the last thing I've been investigating is somehow a more non-commutative example, which is kind of fun, which is a case of the commutator. And so you take a potential and you would like to force your random matrices to commute, and you wonder what is going to happen. Actually, what happens is kind of funny, because when beta is going to infinity, in fact, what we see is that, of course, the matrices will commute, but how do they do that? Or are they going to be diagonal or whatever? And what we could see that somehow the matrices will concentrate also on the minimizer of will commute, but also concentrate on the minimizers of the potential, even though they don't have a big beta to make it happen. So we are trying to find out now what is exactly the shape of this of what is the mass that they can put around each minimizer. But for instance, if you have one potential, which have a unique minimizer, this matrix will be close to identity, but also the other matrix. So this will be enough to make this zero, to make it of reasonable size. But in fact, also the other matrix will concentrate on the minimizers. So that's kind of the funny effects of large beta. Okay, so I think I am done. So to conclude somehow, I think it would be nice to understand better this question of phase transition for matrix model on the low temperature properties, and this is what we are working on. So thank you for your attention.
Thank you, Alice. Thank you very much. And any question? I cannot see all of you, but